Good evening. Tonight we start with something darker, more clinical than my usual stories. The full science of how long awareness lasts after the head is cut off. Forget the Hollywood versions. Slow dramatic cuts and last breaths of fiction. Not real body science. The truth is survival is not the question. Decapitation cannot be survived, but the tiny seconds that follow are ruled by oxygen, blood flow and nerve shutdown. They tell a very clear story. If you like this, take a moment to like the video and subscribe. Tell me in the comments where you are watching from and what time it is there. I'm always curious about where people watch from. Silence your notifications, take a deep breath and let us begin. From river plains where cities first learned to punish and show victory, the act of cutting off a head took on meanings beyond function. In a Syrian palace, art kings trample enemies and show severed heads as proof. A stone certificate of power carved at Nineveh. In those early times, a head on a pole was evidence and warning. Bloody civic record keeping. Proof the city's law was done and the rebel story ended. The same pattern repeats far away. In the Near East and across the Mediterranean, the visible head became shorthand for punishment, enemy closure. Across the classical world, how you were executed spoke of status. In Rome, the difference between crucifixion and beheading was social. Citizens could avoid the slow shame of the cross and get a quicker cut. The show was political theatre as well as penalty. Even the accepted method had moral and legal effects. Early Christian tradition tells of John the Baptist beheading. Later stories of Romans who met the blade, not the cross, carried tragic dignity and hard questions about when life or awareness really ended. Through medieval times, the ritual stayed practical. In England and Europe, the sword and axe were state tools. Their use followed a rough etiquette. The noble might kneel, be hooded, pray and receive the sword. The commoner might hang. Execution was public and formal, an event that drew neighbors, merchants, clergy, children. The logistics mattered. There were blocks and scaffolds attended to hold the condemned, and executioners proud of skill. A skilled headsman was respected in his grim work. A bad stroke could leave a contest of pain and messy fixes. The wish for speed and final, even in a time of spectacle, was oft unpractical. When Anne Boleyn died at the Tower in 1536, Henry VI sent a skilled French swordsman, seen as more merciful and less likely to cause scandal. When Mary, Queen of Scots, met the block in 1587, the ceremony was arranged to reduce spectacle, but still a public show of crown power. By the late 1700s, the question of method shifted from rough hour to Enlightenment values. Public executions were no longer just shows. They faced scrutiny from doctors, lawyers, thinkers, who pondered humanity, law and pain. After the French Revolution, the guillotine arrived, a product of rational reform and industrial efficiency. Joseph Fignus Gillot, in A Doctor and Lawmaker, proposed a humane, equal, mechanized form of death, a device to make executions less arbitrary, less dependent on the hangman's mood. His name stuck in memory. The machine was designed by Antoine Louis, built by German locksmith Tobias Schmidt. Its first public use in Paris 1792. Its later spread during the Terror turned legal reform into a terrifying social spectacle. There was a practical gain in uniformity. One clean cut reduced the uneven skill of axes and swords, but there was an unseen result. The guillotine made executions consistent, repeatable, numerous. Newspapers printed them, pamphlets described them. Eyewitness accounts multiplied. If one said which or I roll was dismissed as a village oddity. Now such things were recorded by many onlookers, sometimes by those paid to examine the result. Doctors, surgeons, executioners kept lists of odd events. Reports began to cluster around strange observations the public could not ignore. Severed heads in bowls or held up to the crowd. Sometimes opened their eyes, sometimes blinked, sometimes grimaced, sometimes moved the tongue. Descriptions varied. Sober doctors tried to separate reflex from thought. Pamphlet writers loved tales of last defiance. The question hardened, touching love, faith and science. Did awareness persist after the blade? This mattered beyond curiosity. Judges and clergy worried if spiritual rites were done right. Lawyers and families cared about legal finality. Was a person really dead when the state said so? Doctors were drawn not just by philosophy, but by the practical problem of human innocence. If pain and awareness could last, then method and speed were not just admin matters but moral ones. The show drew scientists. It offered a rough natural experiment. What happens when the brain supply lines are cut fast? Anatomy and physiology were growing fields. The age of galvanic frogs and early electricity told the educated that twitching muscle did not mean life. The challenge was to apply that to the guillotine. Early observers had conflicting tools. The 1800 seconds produced memoirs and medical reports, trying to weigh eyewitness accounts against biology. The Sanson family, official executioners for generations, left accounts that curious readers studied. Charles Henry Sanson, who executed Louis X. B.I. in 1793, gave interviews mixing professional dryness with dark humor. His records and doctor notes gave raw material for heated debate. Do moving eyelids mean lasting pain or just reflex? The guillotine spread fed the debates. When thousands saw the same odd things, anecdotes gained social force. Then scientists came with scalpels and simple electric devices. They brought a new language for the question. Whether a severed head could feel was not just an ethical riddle. It was a question about the bodily basis of awareness. By the 1800 seconds into the 1900 seconds, neurologists and physiologists mapped the brain in detail. Language shifted from soul, spirit, will to blood flow, oxygen delivery, neuron networks. Early thinkers had no modern EEG, no understanding of the system that sustains wakefulness. They had eyes, notebooks, and a sense that a lip which was not a coherent sentence or a remembered life. Still, their cataloging was valuable. It created the puzzle modern neuroscience would try to solve, to see why those movements do not mean continued inner experience. We must see the brain not as a haunted object, but as a machine with specific energy needs and design dependencies. The brain is famously greedy, a small organ, about 2% of body weight, but it uses a huge share of our energy. At rest it uses nearly 20% of the body's oxygen, and a similar share of glucose. This is not poetic flourish. It is hard biology. Neurons rely almost completely on constant oxygen supply. To maintain chemical balances, reload signal vesicles, reset membranes. They keep only a tiny energy reserve. Unlike muscle, which can work without oxygen briefly, unlike liver and muscle, which stores sugar, neurons rarely have a backup. There are small stores in nearby support cells, but those are limited and slow to use. The specific dance of wakefulness depends on a network, both widespread and energy-hungry. The ascending reticular activating system, a diffuse set of fibers from brainstem to thalamus to cortex, acts as the conductor. It modulates arousal via chemical messengers. The thalamus acts as a relay and synchronizer for senses and cortex. The cerebral cortex is where experience is believed to fall. Sensory details, narrative thread sense of self and others, stitched together by massive thalamus cortex loops. Awareness, as neurologists use the term, requires both the arousal systems that let cortex be receptive, and the cortical networks that combine input into coherent moments. Remove energy support from any part and the machinery fails. The biochemistry of failure is swift. Keeping ionic balances is the most energy-consuming task of a neuron. Sodium-potassium pumps maintain membrane polarization. If energy supplied rupts, the pump slows, then stop. Within seconds, neurons start to depolarize. Synaptic transmission is very sensitive. Signal release and receptor function need calcium balances and energy. When blood flow stops, oxygen in tissue plummets. Energy production stalls and energy levels fall. That collapse quickly silences the brain functionally. Before structural damage happens, it is key to separate these phases. Functional shutdown, loss of consciousness, electrical silence, happens in seconds to minutes. Structural death of neurons which prevent any recovery takes several minutes. Even then, timing varies by brain region and temperature. The delivery system for oxygen and glucose is of fluid dynamic matter. Carotid and vertebral arteries carry oxygen-rich blood into a network of arteries and capillaries bathing brain tissue. Cerebral blood flow is self-regulated within a range of pressures, but it depends on continuity. If arterial inflow is lost, if perfusion pressure drops to zero, capillary exchange stops. There are minor local reserves, oxygen bound in hemoglobin in blood left in vessels right after cutting, a small pool of dissolved oxygen, and little stored sugar, but these reserves are fleeting. In clinical terms, experiments on humans and animals facing total blood loss show consciousness is lost very fast when brain flow stops abruptly. In human cardiac arrest, studies suggest loss of consciousness typically happens within 10 to 20 seconds after effective stop of cerebral blood flow. In carotid compression studies, fainting can start in under 10 seconds. These figures are not exact to the second, but they give a baseline. The brain cannot stay functionally awake long without blood. That baseline lets us translate historical curiosities into a second-by-second story. Imagine the blade falling. The neck contains carotid S, vertebral S, jugular veins, muscles, trachea, a complex web of connective tissue. In a clean cut, the major arteries are disrupted. Arterial pressure to the brain drops fast. The immediate moment is violent in physics, but subtle in physiology. Blood in brain vessels at the instant of separation remains, but the flow that replenishes and brings new oxygen does not. Within the first second or two, some electrical activity continues. Neurons that were active will keep firing as their last charges fade. These last spikes can be synchronized and intense. They are not necessarily the pattern chat that makes experience. They can be terminal fireworks of dying circuits. A burst caused by failing ion balances and chemical release. A second to a few seconds later, synaptic transmission falters. Neurons fail to communicate reliably. As synaptic physical cycling and receptor function break down, the reticular activating system, being energy hungry, is among the first to fail. Thalamus-cortex loops become uncoupled. The cortex stops its coordinated rhythms. Subjective awareness needs integration of signals across areas. A precise dance of timing and frequency. Gamma sync, coordinated beta and alpha rhythms. These patterns fall apart with a speed that is effectively final. For a beheaded person, by the time the crowd notices a blink or twitch, the inner structure making conscious experience is almost certainly scrambled. The feeling of awareness is not the same as the feeling of a reflex. That is not to deny the visible leftovers. The severed head, especially in the guillotine era, was often shown to the crowd or examined by a doctor. Eyes that were closed might open briefly. Eyelids might flutter, facial muscles could contract, the tongue might push out. These movements can look purposeful to an untrained eye. They can even seem to respond to stimuli. Bring a flame near and eyelids withdraw. That impression was perhaps most disturbing, yet nerve anatomy gives simpler explanations. Many eye movement and reflexes are run by brainstem circuits and cranial nerve arcs that do not need cortex involvement. The corneal reflex, for instance, can happen at the level of the pons. A blink may occur even when the cortex is offline. Similarly, facial muscles keep some residual chemical energy and excitability. A final wave of chemical release, a brief flood of ionic depolarization, can make muscles twitch. People of earlier eras steeped in language of spirit and faith could easily read such a contraction as thought. Modern neuropsychology reads it differently. Not a last syllable of thought, but the collapsing echo of complex electrochemical machinery. Animal tests underline the difference between reflex and awareness, though they complicate things by showing species differences. Scientific work in the 1800 seconds showed decapitated frogs could move Nerve-fed muscles could twitch under stimulation for minutes. Galvani's experiments had already shown the public that muscle motion could be separate from inner life. Later, physiologists decapitating small mammals for science recorded a brief period of cortical electrical activity, then rapid stop. In rodents, modern EEG works, adjusts a short surge and high-frequency activity at the moment of decapitation. An electrical storm followed by a sharp decline in silence. Whether that surge means subjective suffering or just the ionic chaos of dying tissue is debated, but the balance of evidence favors the latter. The nervous system is not polite. When denied oxygen, it flares, then goes dark. There are famous outliers in public imagination, outliers that feed hope for gruesome drama. The story of Mike the Headless Chicken, who survived 18 months after a farmyard accident in 1945, is a case in point. Mike's brainstem and 1 ear stayed mostly intact. He was fed and cared for by his owners. His survival shows how in a bird with different brain anatomy, a brain able to handle basic functions with little forebrain, life can persist under odd arrangements. Such examples remind us anatomy matters. The same cut on different animals gives different results. Humans with large energy-hungry cortex and dependence on the reticular, system and cortical loops are not chickens. We should also be clear about the limits of knowledge. Only so much can be known ethically about human decapitation. There are no controlled tests on the conscious experience of a severed head. The main human evidence comes from eyewitness account memoirs. Doctor notes in a historical context often full of political heat and cultural meaning. In contrast, modern neurophysiologists can simulate sudden total blood loss in animals and record the EEG and cell activity with high time resolution. By analogy and inference, we can say with confidence that consciousness goes out quickly, almost certainly within a few seconds, very probably within 10. But we cannot prove beyond philosophical doubt the subjective quality of the final instant. Put another way, the brain's signs of integrated, reportable consciousness vanish fast. Once perfusion stops, any longer-lasting movement is best seen as reflexive, not evidence of sustained awareness. A more technical way to say, it shows why time scales cluster where they do. The sequence runs from blood flow loss to synaptic failure, to electrical silence to irreversible structural damage. Right after arteries are cut, cerebral perfusion pressure drops. Without pressure, capillary flow stalls. Oxygen delivery falls fast. Within seconds, the cell's energy pool starts to drop. Sodium pumps stall in the membrane, potentials collapse. Synaptic vesicle cycling gets inefficient. Calcium builds in cells and toxic processes begin. The EEG, a coarse measure of synaptic potentials across the cortex, shows the synucleation then flattening. Clinically, loss of consciousness follows the fall in cerebral perfusion by a matter of seconds to a few tens of seconds. Electrical silence on a surface EEG usually happens in tens of seconds. The cascade makes the brain unable to have coordinated experience. It is therefore rapid, even if the cellular corpse takes longer to cool. Even the legal and ethical debates that first sparked interest come full circle. Lawyers needed to know if punishment was decisive. Doctors worried about humanism. The public wanted assurance state power was not prolonging suffering for show. The guillotine and its successors answered the first two concerns by trying to be swift and impartial. Modern medical ethics has moved the talk to other areas. How do we measure death? How do we assess pain in those who cannot communicate? What counts as irreversible stop? The historical chase for answers made a clearer picture, but also left a cultural residue. The image of a head, eyes, open staring provokes strong reactions, because the face is the seat of identity. That is why even the quietest medical explanation of reflex can feel unsatisfying beside such a vivid memory from the past. If you step back from the drama and look at anatomy and physics, instead of folklore, the sober conclusion is delicate and firm at once. Consciousness depends on coordinated energy, intense activity. across networks very sensitive to blood flow. Take away perfusion and the network falters almost at once. The physiological machinery of awareness, cortical sync reticular activations, synaptic exchange, fails within a few seconds to at most a short dozen seconds. The muscle twitches, eyelid flickers that made headlines are almost certainly dying echoes of brain stem and spinal circuits, and leftover chemical energy, not the continued presence of a coherent, suffering mind. The weight of experimental neurophysiology points to that conclusion, even as the lack of human, experimental data means the last philosophical doubts cannot be entirely smoothed away. The historical lesson matches the scientific one in tone if not detail. A practice that began as spectacle and power prompted a question only modern physiology could answer. Executioners and doctors, pamphlet writers and lawyers, the crowd at the scaffold and the lab tech with a galvanometer, each played a part in the slow clarification of what ends when a head is cut off. The question that once echoed in public squares has been reduced by science to a matter of timing and metabolic failure. That reduction is not an erasure of meaning. It is an attempt to translate human worry into the language of blood flow and ions. It comforts some and disturbs others. It leaves room for a small arc amusement. The very tool meant to make executions more humane, the guillotine, gathered so many witnesses and oddities that it forced the modern world to confront with uncomfortable closeness what happens in the last small seconds of life's electrical storm. They built the first ones in Paris with an air of civic engineering, a mix of enlightenment, neatness and revolutionary hunger for order. The frame was square and upright, the blade a blunt wedge, honed to a single ruthless purpose. Strangers in dark coats, doctors, executioners, curious citizens, gathered at the scaffold's edge to watch science and justice meet. Joseph Ignace Gallo, the man whose name stuck to the machine, proposed in the National Assembly in October 1789 a standardized quick method of capital punishment. Antoine Louis, a noted surgeon, drew the technical spec. A craftsman, by Schmidt, built the first working sample in early 1792. The first official use in Paris was April 25, 1792, when Nicolas Jacques Pelletier was sentenced and beheaded. Charles Henry Sanson, head of the executioner family, pulled the lever. The sound that followed echoed through generations of reports and rumor. The blade was efficient, the crowds were loud, the doctors leaned in. What those doctors, executioners, anatomists, bystanders described later is a list of small stubborn facts and bigger stories. That eye sometimes blinked, that lids fluttered, that pupils in some retellings seemed to shrink when a torch came near, that mouths opened and lips twitched as if to speak, that a severed head might flush or change expression, that limbs left on a fallen body could keep jerking, and sometimes even make movements that looked, if you were generous, coordinated. Such observations spread fast in newspapers and so on gossip. They were taken as evidence for various moral and medical arguments. Supporters of the guillotine pointed to its speed and predictability, saying the machine removed the cruelty of uneven blows and the long agony of older methods. Opponents stalled counter-stories, homespun horrors of lingering awareness, of heads that registered terror for an instant after the blade. The same events were read through political lenses. Royalists smocked the mechanization of death. Jacobins celebrated its equality. Doctors argued, as they would about any new procedure. And pamphlet writers invented scenes that sold copies. We have fragments of professional testimony from that era. Surgeons and coroners presented executions. Executioner memoirs published later in the 1800 seconds. And countless broadsheets and eyewitness letters, the press of the day. Antoine Louis himself wrote a report, technical, clinical, opinionated. The Sanson family left memoirs detailing decades of official practice. The entries are soaked in the rhythm of a family trade, practical, unromantic. At the same time, the medical community of the late 1700 seconds, early 1800 seconds, did not have the tools we have now to probe consciousness. No electrodoppler array pH, no controlled sensory routine, no standard cognitive tests. They had scalpel's observation and a set of metaphors, animal spirits' electrical excitability reflexes that guided interpretation. To watch ahead for the last flutter of life was for them both a duty and a grim education. When we read these testimonies with modern care, we must use a historian's scalpel. The context of each observation matters as much as the observation itself. Public executions were spectacles with politics in the gallery and money in the pamphlets. Doctors at the scaffold were often medical students or anatomists eager for specimens. Sometimes they were party officials bound to show the revolution's tools were humane. Executioners had reasons to boast of speed and minimize signs of suffering that helped their professional reputation. Opponents of capital punishment had reasons to magnify any sign of remaining feeling as moral evidence. Reports often came second-hand and loud. A bystander's note to a friend, a journalist's sketch for circulation, or a later memoir written when readers wanted theatre more than strict accuracy. Memory is a generous storyteller. Even well-meaning surgeons before modern neurology lacked a working vocabulary to separate reflex from experience, so their notes sometimes read like a ledger of small wonders. A flicker here, a contraction there, whose meaning they could only guess. The medical practices of the era shaped interpretation in other ways. Anatomists and physiologists experimented, and their instruments were theatrical. Electricity, newly harnessed in the lab, offered a way to provoke movement in the dead and dying. The demos were public and persuasive. Giovanni Aldini, a nephew and disciple of Luigi Galvani, took a voltaic device to London 1803. Applied current to the corpse of executed criminal George Forster. Results that hushed the crowd in alarm. Muscle twitches, the face pulled in a grimace, the jaw clenching as if alive. Aldini's shows were not just stunts. They were exercises in what late 1700 seconds, early 1800 seconds natural philosophy called animal electricity. But to an untrained eye, and sometimes even a trained one, such electrically induced movements looked like life returning. They skewed public imagination. Mary Shelley later wove those images into her fiction. The line between demo and drama thinned. Similarly, lab, vivisection, surgical removal of tissues or whole organs from living animals to watch their function, was common among physiologists seeking the seat of sensation. Francois Agent, in early 1800 seconds Paris did spinal cuts and related tests, showing the independence of reflex arcs in the spinal cord. Pierre F. Laurens did aggressive removals of brain tissue to map function. These were not gentle inquiries, but they gave a robust conclusion for their time. That complex behavior, sensation, intelligence were properties of the brain's higher centers, while simple mechanical responses could be sustained by lower centers. The clinical upshot was that a severed head or a brainless animal could twitch and move in ways that misled. That idea entered public talk but took decades and better tools to measure. Those tools finally arrived in the 1900 seconds and later 2000 seconds, as electrodes evoked potentials and carefully controlled animal models. When researchers could place electrodes on an animal's cortex and sample electrical activity before and after sudden isolation from circulation, they began to map the timings of the brain's fading music. Across species, labs reported a recurring set of patterns, an immediate dramatic upset in rhythmic EEG activity, sometimes followed by a brief surge or high-frequency burst, then a relatively fast descent toward electrical silence. In small mammals, especially rodents, this descent often happens on the scale of seconds to a few tens of seconds. Evoked potential signals listed by controlled sensory inputs like a light flash or sound fail sooner for cortical parts, sometimes survive longer for brainstem parts, showing sensory pathways down to lower brainstem, are more resilient for a short time than cortical circuits that support conscious processing. What do these signals mean? It helps to recall what EEG and evoked potentials actually measure. The summed post-synaptic potentials of millions of neurons, flickering in coordination across populations. They are not snapshots of conscious thought. They are the chorus of synapses. An EEG pattern of high sync or certain frequency bands links to wake-up signals on the brain's capacity for conscious content. But these links are not identity statements. Electricity can hum where subjective experience has already dissolved. After the abrupt stop of blood flow, neurons starved of oxygen and glucose start a process called anoxic deprivation. Ions leak membranes, fail synapses, either fire in a chaotic peak, or fall silent as energy reserves run out. Sometimes the earliest stage of this collapse is a burst of disorganized activity, what some studies call a terminal seizure or hyperexcitable wave, lasting several seconds before networks lose the power to organize. That burst can register on EEG as energetic and, to the lay eye, dramatic. It does not, however, necessarily mean continued awareness. It means collapse. Evoked potentials add a bit more nuance when an experiment flashes light at a decapitated animal's retina, or plays a tone the very earliest brainstem level responses. Simple electrical echoes reflecting basic sensory relay may be recorded for a longer window than the higher order later potentials that need wide cortical participation. In other words, lower relay stations can still echo the world for a whisper of time, even as the cortical concert loses its conductor. That fact explains some old accounts of eyes reacting to light after beheading. The retina-endoptic nerve may still transmit briefly. Certain mid-range reflexes that narrow pupils are not guarantees of sentience. The key question for subjective experience, could there be a coherent, reportable stream of thought, is different and harder than a twitch or pupil reflex. Subjective awareness needs global integration across cortical areas. That integration collapses quickly when blood flow and energy support vanish. But it is worth stressing the careful caveats researchers put on extrapolation. Most lab decapitation studies use animals not human. Decades of animal work give consistent patterns, but species differences complicate simple comparison. Small rodents have higher metabolic rates than humans. Their brains use oxygen faster and run out quicker when deprived, tending to shorten the window of survivable electrical activity. Brain size, vascular design, baseline oxygen use change the math. Experimental conditions also matter. In many protocols, animals are anesthetized before decapitation, partly for ethics, partly for control. That anesthesia dampens cortical activity and alters how long residual signals last. The method of cut matters too. Some approaches might leave part of the brain stem intact, or compress blood vessels in ways that change timing. Temperature has an impact. Colder brains use oxygen slower and preserve structure longer. To translate from rodent EEG to human inner experience is therefore to walk on thin ice. Beyond that, and perhaps most importantly, electrophysical signals are proxy measures for experience, not proof. The presence of an evoked potential means the system can still move ions in response. It does not prove a conscious witness. Consciousness seems to need coordinated widespread activity with a particular dynamic structure. Patterns seen after abrupt blood loss and toward disorganization and collapse. Modern measures of such coordination, network complexity or perturbation are responses that neuroscientists use to estimate conscious capacity are not available for the severed human head for good reason. No researcher shouldn't feel to claim that a brief EEG blip after decapitation proves continuous subjective thought. Instead, the literature speaks in careful terms. Residual electrical life for seconds. Brainstem echoes may be a little longer. Cortical integration lost quickly. That is the electrophysical story. The behavioral story is simpler to misread and harder to resist. Human and animal bodies have nerve circuits that can wiggle and move long after the top controller has gone silent. Reflex arcs in the spinal cord work and local loops. A sensory input triggers a motor output without conscious will. Central pattern generators networks in spinal cord and brainstem can produce rhythmic outputs walking, chewing, breathing without cortex command. Animals without brains or with cut spinal cords taught physiologists in the 1900 seconds something they suspected earlier. Movement can be an emergent property of local circuitry. Take a cat with spinal cord cut high in the neck. Under right conditions, hind legs will still make stepping motions on a treadmill. The motions can look purposeful, they are not. That is the key lesson for reading guillotine testimonies. Coordinated lifelike movement does not prove conscious intent. A twitch that looks like a nod may be a stretch of neck muscles, driven by spinal motor neurons reacting to sudden stretch and changing blood chemistry. A facial grimace may be a reflexive contraction of muscles in response to leftover nerve activity. Classic demos of 1900 seconds physiology and older electrical shows show how easily the eye can be fooled. An isolated facial muscle made to fire by electric current gives the impression of expression. We as social mammals are wired to read faces. In a scaffold scene in dim light, watching for an instant, we will almost always read a story the muscles do not intend. Famous historical edge cases dramatize the difference between intact sensation and reflex preservation. The story of Mike the Headless Chicken barnyard accident turns scientific curiosity is instructive. In 1945, a farmer in Fruita, Colorado, beheaded a rooster named Mike and found the bird did not die right away. A part of the brain stem and one ear remained. Mike kept basic behaviors, perching, seeming to eat, under human care for 18 months. Mike was not a conscious man in a chicken's body. He was a bird whose low brain stem function survived and kept key motor patterns running. The anecdote shows that significant behavior can persist without the intact cortex that supports higher thought. It warns against reading human meaning into movement. If you want a principled checklist, what neurophysiologists call operational criteria for when movement might show consciousness, not reflex, the field offers a hierarchy. At behavior level, intentionality is key. Does the organism respond to complex commands? Does it show sustained goal-directed behavior that adapts to new situations, rather than repeating a fixed motor program? At electrophysiology level, one looks for signs linked to awake integrated processing, consistent desynchronized cortical EEG patterns in right frequency bands, long latency, evoked potentials like the P300, linked to attention and stimulus evaluation, measures of widespread effective connectivity patterns, suggesting cortex is communicating across region, not firing in isolated bursts. Newer methods use perturbation AL techniques, briefly stimulating cortex and measuring response complexity across time and space to estimate the brain's capacity for integrated information, a proxy for consciousness. None of these markers are simple, and none are usually available at a hanging or scaffold, but when studied they favor a rapid collapse of the integrative processes that underpin subjective experience after the abrupt loss of circulation. It is also worth saying what the criteria cannot and do not do. They cannot prove silence in any single historical moment seen with the naked eye. They cannot, with current methods, answer the metaphysical question of the last flicker of subjective sensation. They can, however, tell us about probability and mechanism. Given what we know about metabolic dependence, the fragility of cortical networks under blood loss, the speed of terminal depolarization, and the short window of organized electrical activity after sudden decoupling from the heart, it is far more sensible to infer that conscious experience, if it persists at all, vanishes within seconds, not minutes. The lingering motor phenomena, twitching, breath-like efforts, facial movements, are better explained by spinal and brainstem circuits running a short while on leftover chemistry than by a sustained mind in the severed head. So when 1800-second surgeons wrote that the face changed expression, or that eyes shut as if in sleep, They were oft inaccurate observers of phenomena. Their interpretive frames were the problem. A blink was a blink. To take that blink as evidence of experience needed conceptual tools they did not yet have. When Aldine I applied electricity and made a show in London, he proved well that muscle life is not the same as conscious life, but the sight fed public imagination. When an executioner's memoir mentions a head that seemed to look at the crowd, we should note the human context all tales politics gammas, and read the account as a document of social meaning as well as bodily interest. The guillotine era gave us a wealth of eyewitness data. Modern neuroscience gives us tools to read those data in light of mechanism and probability. The lesson that crosses centuries and methods is steady and somewhat consoled in its bluntness. The body keeps moving longer than the mind. Circuits that govern reflex and are the more robust, redundant, distributed. They can often do persist without cortical direction. Electrical life in the brain can linger for seconds. As ionic gradients collapse in an ugly, inevitable way, sensory pathways can echo stimuli as long as there is some leftover driving energy. But the conditions that make thought and sensation possible, stable synaptic links, coordinated large-scale networks, the metabolism of complex nerve machinery, rely on a supply that is cut off the instant after nectar section. Evidence from animal models, clinical studies of blood loss, decades of electrophysiology all point the same way. Short, noisy electrical leftover reflexive, not willed motion, and an end to integrative cortical function measured in seconds, not minutes. If you listen historically, you require to note about the culture of evidence itself. Public executions became for a time a lab without ethics committees, a place where the human body served as object and experiment, where doctors learned to be surgeons, and the public learned to be investigators of a kind, filling notebooks and pamphlets with observations. Later science would shape into testable ideas. The spectacle informed the science, reshaped the spectacle. Galvani STS provoked a scene physiologist, dissected and formalized. Executioners wrote memoirs that sold copies. Each contributed observations, biases, narratives. Our task as scholars and citizens is to separate the strands with as much empathy as accuracy, to honor the human testimony while also reading it against the ledger of physiology. In the small hours when the last candles gutter and lab sleep, the guillotine story rests somewhere between spectacle and science. It is a story of a device that promised humane order and revealed the stubborn complexity of life's final moments. A story that warns us about the persuasiveness of the visible and the need for careful measurement, humility before what we cannot see. It is finally a lesson in how to listen. To the recorded notes of sons and surgeons, to the crackle of an EE in a rodent's quartet, to the slow voices of neurons as they show their last dynamics, and to hold all those voices in the same quiet room, weighing them gentle as a bedside hand until the evidence speaks. The crowd that gathered at the Place d'Ile, our evolution in Paris, could have been mistaken at a glance for a market day. Voices rising and falling like wind through stalls. Children on parents' shoulders. Smell of horses, sweat, cheap wine in the air. And then in the center of all that ordinary humanity, a machine designed to end life as efficiently as a baker chops bread. The year was 1793. The guillotine, a blunt to love egalitarian terror, whose origins traced Joseph Fignes Gallo in 1789 suggestion, and to mechanic by a Schmitten surgeon and one Lewis who built it, had become the symbol of a new public spectacle. Charles Henry Sanson, whose family had executed in Paris for generations, presided over the blade. He later wrote of the work with a dryness trying to make sense of routine. People wrote pamphlets. They whispered, witnesses told stories, and those stories would outlive the facts. If you stand beside a page of those old accounts, the words are a strange mix of precise detail and theatrical flourish. Names, dates, placement of a hand, glint of a blade, woven through with certainty about the last motions of a head just cut off. One observer claims a last wide opening of the eyes. Another swears the mouth formed words. An executioner remembers a grin. A doctor records a symptom, a reflexive blink when the cornea was touched. This is where history meets human reporting, where what people saw what they expected to see, and what they later wrote are braided together in a way that can be mesmerizing and misleading in equal measure. The psychology of these reports is a slow thing, patient as a historian, and as mischievous as the human mind. Under extreme stress on a scaffold, in a trench, in a hospital waiting room, sensory processing narrows. The body throws adrenaline into the bloodstream. Perception amplifies some inputs and dulls others. The Yerkes-Dodson curve is simple and brutal. A little arousal sharpens performance, too much wrecks it. When a Paris crowd waited for the blade, their arousal was not measured. Faces are remembered, lines of clothing, whether the head was pale or flushed. But the finer internal states, whether awareness flickered in that brief gap between blade and stillness, are the kinds of details that slip through memory. Expectation is a powerful lens. By the late 1700 seconds, the guillotine was wrapped in political meaning. To royalists, it was monstrous. To radicals, it was necessary. If you arrive to judge an act you already see as cruel, your senses will favor evidence that confirms the story. The human brain is an expensive, pattern-hungry machine. It trades hours of patient thought for a quick, plausible tale, and then sells that tale to memory as truth. Daniel Kahneman called this system 1. The mind that jumps to conclusions fills missing frames with plausible pictures. System, to the slow skeptical cousin, is rarely in a mob. Then, there is the human tendency to seek agency, to read intention into motion. A twitching eyelid, the reflex closure of a cornea, is easily recast by onlookers into a meaningful nod, a last greeting, a gaze of horror. P. Ryder, lined finding faces in clouds, has a ruthless cousin at the scaffold. Observers sometimes watched involuntary movements and wrote them down as evidence of sensation. A city reporter in London or a revolutionary in Marseille could, in the retelling, polish a reflex into a will depth. The dramatists of the age loved such images. Pamphlet writers sold them. Memory itself is porous and corruptible. Elizabeth Loft assessed research from the 1970 seconds on tortoise. Memories are not static recordings sitting patiently until retrieved intact. They are reconstructions built anew each time we recall, vulnerable to suggestion and reshaping by new information. A witness who hears another version or reads a vivid retelling in the papers may weave that second-hand detail into their own memory as if original. Confidence grows with repetition, but accuracy does not always follow. This explains a lot about why sensational accounts about the last expressions of a severed head have such long lives. They are retold, republished, embroidered, then accepted as fact because the story is neat and the memory sounds certain. Stress changes time too. That slowing of time sensation often invoked in accounts has a physiological basis. The amygdala unrelated structures intensify encoding of key details during fret, and the subjective length of an event can stretch. People who watch a guillotine fall may later swear the interval between blade and silence lasted minutes. To the nervous system, anything that matters seems to last longer. The bet muscle sense does not map reliably to the metabolic and electrical realities of brain function. Culture is a loom on which every eyewitness account is woven. 1600 seconds England had Jack Ketch's name turned joke, an executioner notorious for botched beheadings, whose legend made anything a sadistic twist of fate. In 1685, the Duke of Monmouth's execution was clumsy, needing more than one blow. That bungled moment made stories that spread through London coffeehouses and travelled across the Atlantic. In revolutionary France, the guillotine was both emblem and myth machine. Caricaturist, royalist propagandists, revolutionary newspapers spun tales that made the final moments into parables. Once a trope exists, the head that spoke it is astonishingly sticky. So how does the sensible person weigh a vivid eyewitness account against carefully controlled observation? Start by grading the testimony. Was the observer trained? A doctor writing right after watching and recording vital signs carries more weight than a distant spectator turning rumor into copy for the evening paper. Contemporaneity matters. Notes jotted within minutes are more likely to reflect what was perceived than memories written years later. Instrumentation matters too. A report that includes pulse, breath, or even EEG traces is a different order of evidence than one quoting an emotional reaction. Sample size and reproducibility light of virtue. A single dramatic account is interesting, but a pattern across many well-documented cases is gold. And then a word about the irresistible power of the sensational anecdote itself. Human culture, unlike a controlled lab, rewards storytelling. Newspapers print the vivid piece because it sells. Priests and politicians quote it because it persuades. A vivid but unreliable anecdote will often outlive the dull, precise result from an animal lab. That longevity is not proof, it is simply human nature. Once the mind is primed to prefer story over subtlety, people start to interpret reflexes as awareness and silence as consent. The problem for the modern investigator is twofold. First, to translate what was seen into the language of physiology. Second, to remember that even the best eyewitness is ideologically situated, partial, not impartial. If you let drama monopolize the narrative, full measurements shrink. The sober approach is to triangulate. Let eyewitness reports be hypothesis generators, and physiological data be the confirmatory test. Use the anecdote to ask a precise question. Did the head show a core, kneel reflex? But rely on controlled observation, instrumentation, reproducible experiments to answer whether that reflex fits with awareness. Be skeptical of single reports and generous in the weight you give to converging evidence. When we step out of the theater of memory and into the room of pulses and codes, the story begins to change shape. A living brain is a creature of flow. It is perfusion and fire. Blood delivers oxygen and glucose, and neurons spend that supply. In an electric conversation across networks, consciousness, as neuroscientists now see it, is not a simple flicker controlled at one altar. It is an emergent pattern rising from the thalamus dialogues with cortex, the integrative loops that maintain wakefulness, and the global availability of neural energy. Cut the supply lines and the pattern faltered. How fast it falters depends on supply size, how fast the demand is, and what other routes, if any, remain. To get a feel for the time scales, imagine the brain as a candle in a room of oxygen. The candle burns steadily. It will sputter out when the oxygen is exhausted, but there is a reserve oxygen dissolved in blood bound to hemoglobin, ATP stored in neurons. That reserve buys time, but not much. The adult human brain uses about 20% of the body's oxygen at rest. Cerebral blood flow in a normal adult is around 50 milliliters per 100 grams per minute. Cut the carotid and vertebral inflow cleanly, as the guillotine meant to, and that flow drops fast. Without fresh oxygen, cortical neurons start to fail. First, the high-frequency activity that supports attentive conscious states dims. Then, within seconds to tens of seconds, more widespread depolarization and electrical silence follow. Animal electrophysiology gives the closest experimental window, though with caution that the rodent brain is not a human brain. Studies in small mammals, rabbits, rats have repeatedly shown a brief period after sudden total blood loss, where a burst of electrical discharge surges, sometimes like epileptic bursts, before collapsing into silence. In some experiments, the EEG shows a short high amplitude event, then rapid decline. Timescales vary with species, temperature, and method of blood loss, but many such studies report dramatic worsening of organized cortical signals within a few seconds to a few tens of seconds. Larger mammals with different metabolic rates and vascular design behave somewhat differently, and this warns against a naive one-size-fits-all translation to humans. We must be clear about what we mean by loss of consciousness. It is not the same as the end of all electrical activity. Reflexes can continue without awareness. The spinal cord can direct movements that look purposeful but are not mindful. Eye blinks or grimaces may be brainstem or cranial nerve reflexes. Consciousness properly conceived needs integrated cortical activity and thalamus cortex loops. That integrity is fragile in the face of sudden blood loss. This leads us carefully to practical probabilistic window. No single number can capture the range. Every estimate is within assumptions. So let us set three broad conditional ranges. A conservative lower bound, a middle and a longer bound estimate, each with its assumptions laid bare. First, under the cleanest assumption. Complete cut of both carotid S and both vertebral arteries. Immediate stop of arterial inflow to the brain. Body at normal temperature, no exceptional physiological buffering. The lower conservative estimate for loss of consciousness is very short, on the order of a few seconds. In this scenario, the high-frequency cortical signs linked to awake awareness are disrupted almost immediately. Integrative cortical activity fails within perhaps 2 to 5 seconds. This estimate is conditional and short. It is the best case for rapid loss of awareness. It comes from physiology, no inflow, no oxygen, and rapid fall of neuron function. Second, a middling, more probabilistic window accounts for the messy realities of biological systems. Collaterals exist. The skull and neck hold a column of blood with some residual pressure. The heart may keep generating pressure for a time even if disorganized. There may be partial transient flow into brain vessels through small anastomosis or incomplete cuts. Under these common variations, one could expect loss of coherent cortical activity and therefore awareness. Typically falls in a window of roughly 5 to 20 seconds. In many decapitation models and in considerable extrapolation from cardiac arrest EEG data, the most consistent inference for human cases is that consciousness fades within that range. It captures most well-documented, instrumented analogs and aligns with the bulk of cautious scientific interpretation. Third, a longer bound estimate recognizes rare but real exceptions. If a cut is incomplete, if a carotid is nicked but not severed, if vertebral arteries stay partly intact, or if a gonal heart activity keeps some pressure to the brain, then the window can extend into tens of seconds, and in extreme exceptional setups into minutes. Some animal experiments show organized but pathological electrical pattern that persist beyond 30 seconds. Case reports in Modern Trauma, a literature of near decapitation survivors show that substantial vascular continuity can preserve consciousness and allow survival when surgical repair follows emergency help. These cases are the outliers, real, instructive, rare. Each window carries layered uncertainties. An observer's account of a blink at minute 30 is almost certainly not a direct witness to continuing awareness. The blink may be brainstem. Electroficular correlates of awareness are our best proxies, but we lack controlled human decapitation, EEGs, for obvious ethical reasons. Animal data are instructive but imperfectly scaled. Cardiac arrest studies offer additional analogs. When the heart stops, cortical high-frequency activity fades within seconds to tens of seconds. But the exact map from cardiac arrest to neck cut is not perfect, because vascular and mechanical dynamics differ. Contextual factors matter hugely. Temperature matters. A cold brain uses less oxygen and resists blood loss longer. A warm hypermetabolic brain dies faster without oxygen. Prior hypoxia or intoxicants change the math. A person already hypoxic, drowning for instance, may already have failing cortical function before any trauma. Conversely, a person with extra oxygen store from hyperventilation hypothetically may have minor headroom. These nuances broaden the ranges and warn against blunt certainty. What the weight of evidence lets us say with quiet confidence is this: in the most straightforward, clean, complete decapitation, the neural substrate needed for conscious awareness collapses extremely rapidly, on the order of seconds, not minutes. Sensory report implying prolonged clear perception must be critically examined for reflex misinterpretations, suggestion, or narrative contamination. That said, the existence of credible cases where people with severe but incomplete neck injuries stayed conscious longer, shows the crucial point. Continuity of cerebral perfusion, even if degraded, can prolong awareness and life. The line between perception that flickers out in a few seconds and perception that endures as the vascular tour. If you want practical clinical instruction from this somber calculus, the medical literature on severe neck trauma and near decapitation is where the real lessons live. The 1900 seconds wars and industrial accidents gave surgeons grim experience and eventually life-saving techniques. In World War I and II, battlefield surgeons learned the hard math of airway collapse and hemorrhage. Neurosurgeons and vascular surgeons refined approaches, later applied in peacetime emergencies. The front lines acted as a crude school for what became specialized trauma centers. Control bleeding, secure airway, maintain perfusion. Near decapitation, partial neck cuts from axis machinery, suicide attempts, assault. Present a pattern repeated in case reports from centers worldwide. Patients arrive with airway contaminated or partly disrupted, with massive external bleeding and sometimes with apparently intact mental function. The reason is anatomical and straightforward. The common carotid arteries, though large, can in some injuries stay partly connected. The vertebral arteries may be spared, the trachea and may be intact or only torn. If the brain still gets enough oxygenated blood to support thalamus cortex function, the mind can stay online. Modern clinical care starts where old public executions ended. The immediate priorities are airway and circulation. A collapsed airway will kill even the perfused brain by suffocation. Bleeding will choke cardiac output and remove the pump for cerebral perfusion. Emergency responders prioritize securing the airway, often by tracheostomy when upper structures are disrupted, controlling bleeding with direct pressure and temporary vessel clamping, and fast transport to an operating room. In the OR, the surgical challenge is intense and multidisciplinary. The antivascular surgery, plastic surgery, neurosurgery, anesthesiology all coordinate. Microcirculatory techniques can repair carotid arteries, rebuild trachea, underesophagus, and repair soft tissues. In some documented cases, patients recover with surprising gains, though success is shown to truth. First, continuity of arterial flow is not all or nothing. Partial continuity can sustain consciousness. Second, seconds in the pre-hospital phase become hours in the OR, then months in rehab. Neurologic outcomes depend not just on the moment of injury, but on total time the brain spent under low perfusion, and on resuscitative measures applied quickly after. The spectrum of outcomes is wide. Some survivors walk away with relatively intact cognition after dramatic repair. Others suffer hypoxic brain injury from the interval of low blood pressure and show severe deficits. The most instructive cases in the literature are those where meticulous documentation shows the path from injury to resuscitation. Pre-hospital airway secured, bleeding controlled. Imaging showing patent or injured vessels. Surgical anastomosis restoring flow. And a post-operative course that decides recovery. These reports are both clinical triumphs and warnings. They show the possibility of life and the fragility of brain survival. One particular injury gives especially clear data. Penetrating neck wounds where imaging shows one intact carotid on one side and a severed other. These cases show how much a single artery supported by the circle of Willis can preserve consciousness. The circle of Willis is the brain's roundabout for blood. It lets flow from one side redistribute to the other in the right conditions. If the circle is open and a carotid remains, the brain can be perfused unevenly, but enough for a time. This is not guaranteed and individual anatomy varies a lot, but it is one mechanism by which partial continuity translates into living awareness. Clinical lessons also stress that the presence of apparent voluntary movement is not a reliable sign of intact awareness. Limb motion and facial grimaces can be spinal or brainstem driven. Pain reports often cited in historical anecdotes are also unreliable in some cases. A conscious patient may report pain, an unconscious one will not. Careful neurologic assessment when possible and imaging are needed to separate reflex from reason. If you compress the clinical teaching into one dry sentence, it would be this. When the neck is breached but vascular continuity is kept, the brain is vulnerable but survives. When the vasculature is severed, the biochemical machinery of consciousness shuts down fast. The difference is physiological mechanics, not metaphysical drama. And so the historian's steady lamp and the clinician's quick tools meet. The stories of blinking heads and last words, of which there are many, and which are often moving, must be read with the twin keys of skepticism and empathy. Skepticism because the mind is fallible and science demands rigor. Empathy because witnesses are people shaped by fear and hope, and because the human impulse to tell stories is not a vice but a survival strategy. Remember to the irony. The guillotine was invented to be humane, to make death quick and equal. It became instead a crucible for human narrative, a machine that produced not only severed lives, but also an array of tales, some useful, some fanciful, all human. In the end, physiological story, arterial flow, oxygen debt, neural depolarization, speaks the gentlest truth that without blood, the machinery of awareness fades quickly, often in seconds, sometimes in tens of seconds, and only rarely in the presence of partial vascular continuity might it last longer. The capacity for precision we now have comes from centuries of careful anatomy electrophysiology, wartime learning and painstaking clinical reporting. The capacity for storytelling is older still, and it will keep shaping how we remember the unthinkable. Live with that, a quiet fact wrapped in a loud history. The empirical windows are narrow, the anecdotes are wide. Science asks for caution, history insists on texture. Both together give the most honest picture that human perception and human physiology are different things, and that the truth about those last moments is often somewhere between the willing ear of the teller and the impartial beat of the heart. Forensic medicine treats catastrophic neck trauma as an exercise in translation. The body is a plain but reluctant witness. The wounded script, and the doctor, before judge or coroner, must read that script aloud, with care, humility, and awareness of what cannot be known. In practice, this reading folds together scene, mechanism, physiology. A decapitation, a crushed cervical spinate, also to orn away at the neck. These are not mysteries to solve by guesswork, but puzzles to assemble from fragments. The angle of the cut, the instruments, the environment, body position, hemorrhage pattern, presence of clothing, temperature and rigor of the corpse, statements of eyewitnesses, seen through the measured lens of modern medical investigation. Questions about how long someone stayed conscious after catastrophic neck injury are never answered by spectacle. They are answered by triangulating biological plausibility with observable signs and the limits of inference. The coroner's office gathers evidence, like a careful reader, not to produce drama, but to follow standards courts will recognize, and families will have to live with. History teaches that courts and coroners have long leaned on medical testimony in cases where death came by the neck. In England, the office of coroner, created in 1194, slowly became a node where legal questions about sudden violent death met whatever local doctor or surgeon could be called. By the 1700 seconds and 1800 seconds, as medicine professionalized, doctors took a more central role. They were called to the scaffold not only to cut the cord of life, but to certify its severance. The guillotine story in revolutionary France shows the uneasy marriage of medicine, law, and public hunger for certainty. In 1789, Joseph Ignace Guillaume, a member of the French National Assembly, proposed a standardized, ostensibly more humane form of execution. The device linked to his name was made real by doctors and mechanics, notably Antoine Louis, who lent anatomical knowledge. By 1793, it became the instrument of public punishment. Charles Henry Sanson, executioner of Paris, carried out Louis XV's execution. January 21, 1793. The tool would be used thousands of times after. Newspapers, pamphlets, doctor reports began to air a peculiar concern. Had the guillotine ended consciousness instantly, with the heads of the executed still thinking as they fell into the basket? These questions, partly scientific, partly theological, pushed doctors into the role of expert witnesses, asked to translate physical observations into statements about subjective experience. Those doctors and surgeons did not work in a vacuum. Across Europe, physiologists in the 1800s probed the nervous system with experiments that would inform later forensic judgment, if imperfectly. Marie-Jean-Pierre Eflarens in France in the early 1800s did controlled removals and watched reflexes in pigeons and rabbits, charting what remained when the cerebrum was gone, and what stopped when brain stem or cerebellum were damaged. His lab was stark and methodical, a place of careful scalpel cuts and dashing notes, not melodrama. His observations helped later generations tell reflexive spinal activity from the integrated cortical processes we link to awareness. In Victorian England and the new field of forensic pathology, figures like Sir Bernard Spilsbury would later take the magistrate's bench by storm, translating pathologic findings into courtroom verdicts with great social weight. When Spilsbury testified in early 1900s high-profile cases like the Crippen trial 1910, his authority helped shape the public idea of what medical testimony could resolve. But that authority, like any human authority, came with blind spots. Confidence can become shorthand for certainty, and the law demands precision where medicine often offers probability. Modern forensic practice has learned to be more modest. The medicologo approach to timing of death and interpretation of post-injury signs accepts that in catastrophic neck trauma the mechanism itself is often decisive, but it also sees physiological detail and evidentiary limits. In any medicology investigation, the first step is practical. Secure the scene document, everything photographed from many angles. Record witness statements, transport body and evidence to the post-mortem suite. Classic tools for estimating time since death. Body cooling, alga mortis, post and stiffness, rigor mortis. Settling of blood, live or mortis, the chemical clock of potassium and vitreous humor. Gastric contents, insect colonization remain useful in ordinary cases. In catastrophic neck injuries, these markers are secondary to the main question of mechanism. A complete cut of cervical spinal cord and major vessels is by anatomical necessity incompatible with prolonged brain perfusion. The modern legal standard for declaring death in many places, the Uniform Determination of Death Act in the U.S. 1981, recognizes either irreversible stop of circulatory and respiratory functions, or irreversible stop of all functions of the entire brain, including brainstem, as legal death. That legal language is a distillation of decades of physiological and ethical debate, not an answer to every forensic nuance. Physiological realities narrow, but do not close the window of uncertainty. Consciousness depends on integrated cerebral cortical activity and adequate cerebral blood flow. Severance of the neck normally removes the head from its arterial supply. Arterial pressure collapses, oxygen delivery stops, and cortical neurons' voracious oxygen users begin to fail. But the brain is not a single clock that flips instantly. It is a collection of tissues with different metabolic needs and susceptibility. Residual oxygen in blood within the skull, temporary gas diffusion and partial circulatory continuity. If the cut is incomplete or major vessels are compressed, not cleanly cut, can all extend cortical electrical activity for a brief interval. Forensic investigators therefore speak not in absolute certainty, but in well-bounded probability. The physiology suggests a rapid loss of consciousness, most likely within seconds, though the exact number cannot be known from external observation alone. This probabilistic stance explains why courts have historically relied on medical testimony, and why those testimonies have sometimes been both decisive and contested. When a judge or jury asks whether a person felt pain in the moments after catastrophic injury, The medicology expert must translate neurophysiology into courtroom language within a reasonable degree of medical certainty, or it is likely, while explaining the assumptions behind such statements. The law has developed its own grammar for scientific evidence. In American law, the Frye Standard from 1923 first governed admissibility, with a general acceptance test, later replaced in federal courts by the Daubert decision 1993, which stressed the trial judge's gatekeeper role in assessing scientific validity of expert testimony. Similar changes happened elsewhere. These legal doctrines force forensic medicine to be explicit about methods, error rates and limits of inference. A pathologist cannot simply say he was unconscious immediately, without explaining what observation, measurement, or physiological principle supports that. Forensic practice therefore layers different kinds of evidence. Investigators will document the weapon and mechanism, photograph and measure the neck wound, do radiographic imaging to understand trajectory and depth of injury, take toxicology samples to assess intoxicants that might have changed responsiveness. At autopsy, the pathologist will document lacerations, examine vertebrae and spinal cord, trace hemorrhage patterns, sample tissues for histology that may show pre-mortem vital reaction, bleeding, inflammation, as distinct from post-mortem artifact, where there is a question of residual brain function at time of separation. Neurophysiology can show if the cut was clean, and if vascular structures were occluded before stimuli ceased, but it cannot read subjective experience. Electrophenologically, EEG and other neurophysiological tools can measure cortical activity, but their use in medical decapitation cases is limited. Post-mortem EEG in humans is rarely available in real time, and if gotten seconds after injury, it may still miss a brief unrecorded interval of residual activity. Courts must thus be taught the difference between observation and inference, between a recorded electrical waveform and the question of what did the person feel. There is a further layer of interpretive caution that shapes forensic testimony. Reflexes. The human body runs onto tracks volition and reflect, and the latter persist after the former is gone. Spinal cord circuits and brainstem centers mediate many automatic responses. At autopsy and at the scene, examiners will sometimes see kicking limb withdrawal, or phasic movements that can look to untrained eyes like purposeful action. The dispassionate forensic clinician knows these as spinal or brainstem-mediated phenomena, not evidence of continuing subjective awareness. The same applies to our responses and facial twitching. In the early 1900 seconds, such movements were sometimes misread in sensational press accounts and even in legal testimony as evidence of prolonged consciousness. Modern pathology, backed by decades of neurophysiology, resists that jump. The conclusion is pragmatic. Forensic testimony should explain that reflexes can mimic life, and that such mimicry cannot be equated with lasting awareness without corroborating physiological data. This is in important ways an ethical as much as technical stance, and it is the hinge on which the conversation turns. Toward execution practice, medical testimony, and the limits of research. The moral questions are old. When Joseph Ignace Gallo proposed a codified, ostensibly more humane execution method in 1789, his stated goal was to equalize and humanize a system that had become public spectacle. He could not have imagined how his name would be forever joined with the device that came to represent that modernist promise. Yet, even as the guillotine worked in public squares, critics asked whether mechanized efficiency is the same as humaneness. If a method ended life swiftly and without detectable reflex, was that humane? If it did not, should doctors have a hand in its design? These are not just rhetorical questions. They shaped legal reforms and professional ethics. By the mid-1900 seconds, the medical profession and international law had begun to formalize boundaries. The horrors of non-consensual human experiments under totalitarian regimes prompted the Nuremberg Code in 1947, The Helsinki Declaration of 1960 for refined principles for medical research. Later versions keep guiding research ethics. Codified policies in professional groups followed. Doctor groups in many countries said participation in executions was inconsistent with the doctor's role as healer. In the United States, the American Medical Association, reflecting a broader shift in medical ethics long ago, concluded doctors should not take part in capital punishment in ways that facilitate death. The reason is not a quaint attachment to abstract ideals. It is practical and moral. When a doctor lends medical skill to the mechanics of killing, medicine's authority becomes an instrument of state power in a way that erodes public trust and compromises the healing mission. The practical result seen in recent decades has been a scramble by states seeking medically credible lethal injection protocols. Because doctors refuse to be involved, states sometimes turned to paramedics, pharmacists, some credentialed technician, creating protocols less transparent and more legally vulnerable. Research faces sharp ethical limits. The simple fact is no ethically approved experiment can sever a human neck to watch subjective experience. The Nuremberg Code, the Helsinki Declaration and modern review boards are clear. Experiments that intentionally cause death or serious injury to human subjects are not allowed. That moral boundary forces scientists to rely on animal models and observational inferences about human physiology. Animal experiments have value. They have shown how fast cortical activity collapses when blood flow stops, and they have distinguished reflexive motor patterns from integrated cortical processing. But they cannot fully settle questions of human subjective experience. Differences in brain size, metabolic rate, and anatomy matter. Small mammals, for instance, use oxygen stores quickly and may show a different pattern of residual activity than a human brain with its different blood volume and design. Modern research ethics tries to balance the scientific question with animal welfare by demanding strong justification, minimization of suffering, and use of the smallest number of animals possible, overseen by institutional animal care and use committees. It is a compromise full of moral tension, but it is the compromise democracies have agreed on, so the pursuit of knowledge does not become an excuse for cruelty. Clinicians and scientists working in this space therefore have special responsibilities. First, they must be scrupulous in how they present findings, especially before courts or public audiences. Overstating certainty creates legal and moral hazards. Understating the significance of plausible harm creates different ones. The medicology expert must explain the contours of uncertainty, what the physiology makes likely, what it makes impossible, and where gaps remain. Second, the professional must recognize the social impact of testimony. In capital cases and reform debates about humane execution methods, in legislative committees weighing punishment policy, a pathologist's words can carry decisive weight. That is a reason for greater humility, not for silence. Expert knowledge matters precisely because it limits error and stops rhetoric from pretending to be evidence. Third, clinicians must guard against becoming instruments of a state's machinery of death. The history of medicine has some steps where doctors let themselves be conscripted into harm. Ethical codes exist because those missteps leave scars. These medicology and ethical realities help demystify the elaborate myths that fill popular culture. Art and commerce have always found the image of decapitation alluring. Film, literature, folklore feed imagination with pictures that stretch physiological reality for dramatic length. Monty Python's Black Knight refuses to accept anatomy for a laugh. Comedy at its most gleeful and chiding. George R. R. Martin's TV show, when it showed Dead Dog Ned Stark's execution in 2011, lingered visually on the fall, the close-up of the face, the aftermath, in a way that sparked much online talk about whether it suggested continuing awareness. Timeless folk tales, Washington Ness Headless Horseman from the early 1800 seconds, trade in supernatural, not physiological truths. Hollywood novels make art of extended farewell, but art and evidence are different kinds of honesty. Why do these portrayals stick in the public mind? because film is designed to slow reality for effect. A director will hold the camera on a human face for several cut breaths to let the audience register loss. The screen cannot show an instantaneous stop and still leave room for viewer emotion. Reflexive post-mortem movements and brief eyelid openings, both recorded in fragmented historical anecdotes, are amplified into sustained volition on screen. Newspapers to have historically given oxygen to such stories. Sensational accounts of guillotine executions in the 1800 seconds, early 1900 seconds. The odd report that a head opened its eyes or tried to speak was copied across papers, feeding a collective sense that the decapitated might linger. There was even a recurring anecdote in medical and popular literature of early 1900 seconds French doctors seeing brief eye or face movements in a guillotined head. Historians of medicine pass such accounts as instances of short-lived reflex activity, sometimes plausibly exaggerated by witnesses and recounted with flair that sold papers. Science responds to myth in three ways: by testing what can ethically be tested, by explaining what cannot be tested, and by translating complex probabilistic judgments into language the public and courts can use. The testable part, anomaly, e.g. after rapid blood loss, histologic signs of pre-mortem reaction, biomechanical assessment of cutting forces, has repeatedly confirmed that the conditions needed for sustained conscious experience collapse quickly when the neck is catastrophically severed. The untestable part, the private experience in the last instant, remains the province of agnosticists. Good medicine does not pretend to reach where it cannot. That posture is not obfuscation, it is integrity. So when film trickery shows eyes that stay clear, and lips that form a last coherent sentence, the responsible historian and clinician smile, quietly correct the error, and then explain why the image is so seductive. Reflexes are not feelings. Electrical storms in a dying brain are not the same as the integrated narrative we call subjectivity. The nervous system can make complex-looking motions without the person being there to see them. The law recognizes this complexity in the phrases it borrows from medicine. To a reasonable degree of medical certainty, more likely than not to irreversible cessation. Those are the frames courts accept testimony in, and they are the frames forensic pathologists must speak within. There is a last softer truth before we move from science back to story. These technical debates always sit beside the larger human questions of dignity and grief. Families do not ask pathologists for sterile certainties. They ask for explanations they can live with. Societies do not make penal codes for their own sake. They do so to express collective values about justice and deterrence. When science is used to justify an execution method, or soothe worries about what happened in a final instant, doctors become translators not only of physiology, but of social ethics. Their duty is therefore not just to be careful in the lab or autopsy suite. It is to be candid and public, to resist being enlisted in policies that would use medical knowledge for needless cruelty, and to support research that reduces suffering wherever that research can be done ethically. Popular myths will persist. They will be retold on stage and screen, exaggerated by rumor and myth, because they touch primal fears and questions modern life has not fully tamed. But medical legal practice anchors the conversation in a different register, one of method, documentation, probabilistic honesty. It tells courts what the evidence supports and what it cannot show. It tells families what is likely and why without promising sensation where no proof exists. And it reminds policymakers that medicine's authority is precious, earned by restraint as much as by knowledge. In the end, the tale the scientist and storyteller must agree on is modest and humane. The physiology signals an abrupt end to integrated consciousness. When the neck is catastrophically severed, the precise texture of any last instant is inscrutable, and for ethical reasons unprobable in human experiment. Reflexes and electrical blips are not the same as subjective experience. Courts must be guided by careful testimony that acknowledges limits, Doctors must refuse to be drawn into roles that make their craft a tool of execution. Researchers must pursue knowledge within constraints that respect life and dignity. And as for the myths, the blinking eyes, the whispered last word, the head that knowed, they make fine stories around a fire, even as we, with the steady light of science and the steady light of ethic, tell a truer, one brief, probable and merciful in its honesty. What remains unresolved, stubborn, oddly intimate, is how to translate a handful of animal experiments, a century of executioner notes and a scattering of clinical analogues, into a reliable timeline for human consciousness after complete decapitation. The past gives stories. Joseph Ficnus Gillot, a doctor in Paris, who in 1789 proposed a more egalitarian instrument of death. Antoine Louis and Cabinet maker Tobias Schmidt, who turned that idea into a machine. The Place de la Evolution, crowd January 21, 1793, when Louis XV, his passing was noted and recorded, the guillotine thereafter becoming both tool and symbol. Through the reign of terror, through the 1800 seconds into modernity, until Hamid Age and Alba's execution in France, September 10, 1977, the last of Western Europe's guillotines. Each app a cleaving notes, eyewitness accounts, and sometimes a doctor's observation from the scaffold. These are the sources historians turn to when we want to know not just what was done but what was understood. They are also the sources that make modern scientists uneasy, fragmentary, biased, imprecise, human. The first and most obvious gap is the lack of ethically obtained direct human physiological data. You cannot and must not design an experiment where a person's head is severed to time their subjective experience. That is settled law and settled ethics in modern democracies. Our data are therefore pieced from proxies, animal experiments, clinical events like cardiac arrest or traumatic cuts, historical forensic descriptions, and when available well-documented medical observations. Each proxy brings its own distortions. Animal experiments give controlled measurements, but the species differ in size, vascular anatomy, metabolic speed. A rat is not a person. Clinical analogues like sudden cardiac arrest tell how fast a human brain fails when perfusion stopped, but those events are not clothed in the same mechanics as instantaneous electroresection. Forensic and historical records give human voices vivid, compelling, but they arrive filtered through the cultural languages of their time, the theater of public execution, audience expectations, an executioner's desire to reassure or frighten. Species differences are more than a cautionary footnote. They are a central part of the uncertainty. Rodents have much higher metabolic rate per gram of brain tissue than primates, so neurons run hotter and use fuel faster. They also differ in skull shape and neck vessel arrangement. The vascular design feeding human cortex is unique in its pattern of carotid S vertebralescent, the circle of Willis, and the network's behavior at the moment of catastrophic cut cannot be perfectly mirrored in a pig or rodent model. Some mammals have vascular specializations like a rat that change pressure dynamics at the skull base, a detail that makes extrapolation risky unless explicitly accounted for. Even between pigs and humans, where pigs are often used for size and organ similarity, important differences remain. The spatiences of the human skull, the relative mass of cerebral tissue, the human brain's reliance on constant, finely tuned perfusion, all makes simple scaling arguments unreliable. Electrophysically, otherwise our clearest window into neuron life and death, brings its own interpretive limits. An electrophican luster echoes coordinated electrical activity across populations of cortical neurons. It is a measure of sync and pattern, not a direct index of subjective experience. Flattening of the EEG suggests loss of organized cortical processing, but it does not prove absence of conscious experience in the final seconds. Conversely, isolated spikes or local field potentials do not necessarily mean a coherent reportable awareness persists. Brain stem circuits may fire independently, producing reflexes that look purposeful to an untrained eye. Pupil changes to corticate postures, spinal movements after transection can be made by residual brainstem and spinal cord activity. They are not reliable proxies for subjective suffering. The language of isoceltica and flatline itself misleads. Unless we remember the EEG is sensitive to electrode placement, muscle artifacts, hypothermia, electrical noise, records taken in 1900 seconds execution yards when they exist, are oft unqualitative descriptions, eyes open, cheek blushes at witch, not continuous high-fidelity neurophysiological traces. Modern instruments could do better, but ethics largely prevents the human experiment that would settle the question. Yet the scientific mind persists. Within ethical boundaries societies set, there are clinically and legally responsible ways to reduce uncertainty. One path is retrospective forensic analysis. Execution records, coroner notes, hospital trauma charts, sort autopsy reports are the slow treasures of this work. Documents that tell where doctors stood, exactly what they saw and wrote, and how such observations were shaped by protocols of different eras and places. Francis Long Guillotine Use Made Archive. British and German execution practices left reports. 1800 seconds doctors recorded immediate reactions to decapitation in ways that, while imprecise, can be gathered, coded, analyzed with modern statistics. A careful prerequisite study could assemble these scattered records, apply clear criteria to assess reliability, correct for eyewitness biases, and map patterns. This is not a path to measuring consciousness directly, but it is a legitimate, ethically safe way to narrow descriptive uncertainties about what observers consistently reported, until the modern era made their practices obsolete. Another ethically acceptable route lies in better, principled animal models. The work must be designed with three priorities: minimizing suffering, maximizing translational value, rigorous oversight. That means using species whose anatomy better matches human cerebral perfusion, like larger mammals, but only under protocols with proper anesthesia and analgesia, so no avoidable pain occurs. It means designing experiments that do not recreate human execution for spectacle, but that isolate mechanisms. How fast does cerebral perfusion fall when major neck vessels are cut? What happens to tissue oxygenation and glucose at 1 second, 5 seconds, 10 seconds? Which patterns of electrical failure are reproducible? It means using modern monitoring, intracerebral oxygen sensors, near-infrared spectroscopy, multi-channel and electrophysiology with carefully calibrated reference tissue, and then interpreting those signals with humility. This is science, not theater. The goal is to map processes, not court headline numbers. Ex vivo approaches offer another ethically safer corridor. The 2019 work from Yale University, led by Nina Tsaist and colleagues in Nature, showed that microcircuitally unsynaptic functions could be restored in pig brain cells after slaughter using a perfusion system, now known in neuroscience circles as Brain X. That experiment did not restore consciousness, and the author's work clear about limits and ethical boundaries, but it showed brain tissue metabolic viability can be partly preserved, and that complex cell functions can outlast circulatory death under certain conditions. Experiments that refine ex vivo perfusion not to awaken, but to understand biochemical timelines and thresholds for synaptic failure, provide a path to knowledge that does not raise the moral specter of reanimating a person. They allow detailed measurements of ionic gradients, mitochondrial function, and the sequence of synaptic breakdown under exquisitely controlled conditions. They also raise the ethical question of where to draw the line. If an ex vivo brain starts to show coordinated electrical activity, does oversight require its end? The answer must be set not only by scientists, but by ethicists, legal scholars, the public. Complementary to wet lab work is computational modeling. Informed by human anatomical data, we can model the hydraulic and metabolic collapse that follows neck transection, the instant loss of arterial pressure, the drain of blood from cerebral microvessels, the oxygen reserve and hemoglobin, the time constant for neuronal depolarization when ATP runs short. These are biophysical problems amenable to simulation. A model that integrates human vascular geometry, known kinetics of neuronal oxygen use, and empirically measured thresholds for synaptic failure, could produce probabilistic timelines, not absolute certainties. Such models must be validated against animal data and tuned for human-specific features like brain size and the circle of Willis. They cannot and will not create subjective reports from thin air, but they can shrink the realm of possible answers into narrower windows, which is exactly what prudent science should do. Human cadaver studies and high-fidelity surgical simulation may also help. Cadavers preserved with techniques that keep vascular pliability and tissue integrity can show in explicit detail which vessels are cut in a given neck injury, how surrounding connective tissue behaves, and how much potential for collateral perfusion exists anatomically. These are descriptive anatomical data that refine models of physiological failure. They are ethically acceptable with proper owner consent. Similarly, simulated surgical environments, where clinicians test hemostatic devices and vascular clamps, offer chances to instrument neck vasculature, again, improving our models without harming living subjects. Any path that seeks to reduce uncertainty must be wrapped in rigorous ethical oversight. Institutional review boards and equivalent ethics committees must be involved from the design phase. Animal experiments must be judged by institutional animal care and use committees, and meet international standards like EU Directive 201/1063 EU, or the UK Animal Scientific Procedures Act 1996 depending on jurisdiction. Old debates the Cruelty to Animals Act 1876 that marked Britain's early vivisection regulation, the Animal Welfare Act of 1966 in the US, and the evolving European framework are not museum relics but living structures that shape what is permissible. Beyond formal regulation there must be transparency. Pre-excitation of hypotheses date, a sharing so claims are verifiable. A multidisciplinary oversight board including neuroscientists, clinicians, ethicists, historians, public representatives would be wise, especially for research near the boundary of consciousness studies. The study design should include stop criteria agreed in advance. If investigators find coordinated activity patterns that could plausibly indicate integrity of brain function, the protocol will require consultation and, if needed, experiment halt. There is finally a place for public engagement. Questions about death touch culture, religion, law. Any research program investigating the boundary between life and death should not proceed as if the public were just an audience. It should be in dialogue with communities whose values and anxieties it will affect. We move now gently from what we might study to how we should speak about it. The way subject is narrated often shapes its social life more than bands of data tables. There is an ethical responsibility in communicating violent science that is not reducible to don't show bad images. It demands journalists, filmmakers, educators, scientists recognize the human charge of this topic and act accordingly. First, language matters. Words like beheading and decapitation carry different tones. Decapitation is clinical, geometric, neutral. Beheading is moralized or ritualized. Severance of the cervical spinal cord and major vasculature is precise. The head lived for X seconds is not precise and can mislead. Avoid metaphors that imply prolonged subjective experience, unless you can justify them with data. Resist the temptation to use sensational phrases. Screamed silently, the mind lingered, he saw the lights. These are narrative flourishes that feed myth more than understanding. Use probabilistic language. Evidence suggests the most likely window. We cannot exclude a brief interval. Signal uncertainty as part of the story, not a failure of expertise. Trigger warnings are not just courtesy. When an article, film, lecture touches graphic depictions of death, especially beheading, warn your audience at the start. Explain the nature of the content and the intention behind it. For viewers with trauma history, such content can cause distress. The responsible communicator provides ways to proceed or opt out. This should be standard in educational materials. Content notes before potentially upsetting units in medical or history courses. Optional modules for sensitive viewers, alternatives for students who prefer a less graphic path to the same learning outcome. Storytellers must also choose visual and narrative techniques with care. Archival photos of public executions have historical value, but show them with context, not as gore for its own sake. Reenactments can avoid explicit visual violence by implying the act. A closing of the camera, a lowered sound cue, a shot that lingers on audience's hands, not the instrument. Animations explaining blood flow and oxygen depletion can be more informative than a blade close-up. If you must show a body, prefer silhouette, shadow, or objects linked to the act. A fallen shoe, a bloodless cloak, the executioner's gloves, rather than the primal image itself. Films that lean on gory detail do two things. They titillate and they mislead. They make viewers think they understand when they do not. For journalists, the ethics of sourcing and verification is key. Find scientists who can speak about limits and place those caveats prominently. Interview historians to frame how past societies understood these events. Consult ethicists to unpack why certain research is not done. Avoid headlines that compress nuance into oversimplified claims. Victims conscious for minutes after execution sells, but is almost always wrong. If your piece draws on historical accounts, identify their context. Who recorded the observation at what remove with what possible bias? If reporting on new scientific work, ask about sample size, species used, monitoring techniques and whether methods were pre-existed. Demand clarity. Were subjects anesthetized? Was perfusion measured directly? How was consciousness defined? Filmmakers must remember cinematic truth and scientific truth are rarely the same. A sure way to inform without causing needless shock is to focus on consequences and meanings, not mechanics. Tell the story of a city trying to legislate an execution method. The municipal debates over humane devices in late 1700s Paris. The political theatre of the scaffold. Use sound design and pacing to suggest tension, not explicit imagery. If you dramatize medical testimony, show the uncertainty. Let a doctor in period costume explain the limits of observation. I saw the eyes flutter, but I could not tell if they were seeing. That is human and responsible. Educators have a special duty because they shape future professionals. In medical schools, teaching about death and decay should come with ethics modules and mental health support. Use simulations, not graphic live displays. In history classes, contextualize eyewitness accounts. Teach students to read them critically, to understand the rhetorical moves of public spectacle. Encourage assignments that need cross-disciplinary reading. A historian's archive, a neuroscientist's methods paper, an ethicist's position statement. Scientists themselves must polish their public speech. Avoid grand extrapolations from narrow data. If an EEG flattens in an anesthetized pig 5 seconds after cut, do not turn that into a confident statement about unanesthetized human experience. Be explicit about limit speak in probabilities and ranges. Explain what variables could shift those ranges. Anticipate sensationalism and address it publicly. When a journalist asks for a one-line quote or for a line of science, not a dramatic aside. If your work bears on topics the public finds morally fraught, engage ethicists surely and publish with clear, accessible explanations of what you did and why. Finally, always center dignity. The dead and the public that remembers them deserve explanations that do not exploit. History is full of instruments that promised efficiency and equalization and delivered spectacle. Modern science must resist the old temptations to turn human suffering into entertainment. We can be precise, humane, and, yes, even plain-spoken. Clarity and simplicity need not be cruel. If you will forgive a final step back from microscope and camera, Let us hold the strongest conclusions gently in hand. The preponderance of evidence from animal electrophysiology, from clinical experience in sudden cardiac arrest, from careful physiological reasoning about oxygen delivery and neuron metabolism, converges on a sober inference. When the head is completely cleanly separated from the body, the brain loses organized access to arterial blood flow almost instantly. Cerebral perfusion halts, oxygen in cortical capillaries plunges, and neurons start to fail. The sensory world, those neurons could build, collapses rapidly. In many controlled animal experiments, EEG activity consistent with organized cortical processing collapses within seconds to tens of seconds. In human clinical analogues, like sudden loss of cardiac output, loss of consciousness often follows within a handful of seconds. Taken together, these lines of evidence argue strongly that sustained reportable conscious experience lasting minutes after complete decapitation is highly unlikely. Yet we must not let the pragmatic clarity turn into an absolute. We cannot measure subjective awareness in a body that is gone. The reports of fleeting reflexive movements, of eye blinks or a flushed expression are real in the sense people saw them. But physiology and neuroanatomy warn against treating those signs as continued consciousness. Brain stem and spinal circuits can produce striking coordinated outputs that look like animal life, but are not integrated reportable cognition. And several contextual variables complicate any attempt at a single number. The completeness of the cut, whether some tissue or small vessels stay intact, the speed arterial pressure dissipates. Pre-existing physiological state, was the person hypoxic, anesthetized, intoxicated, and species-specific anatomical features that change perfusion dynamics. For those reasons, the best scientific statement is not a rule but a probability. Rapid loss of consciousness within seconds is the most likely outcome. A brief residual interval of disorganized reflex activity is not implausible. Prolonged awareness is improbable. This is a science that lives in margins and near edges, entwined with history, law, ethics. The guillotine story teaches something about modern science's obligations. It was introduced as an egalitarian instrument, clinically rationalized by men in powdered wigs, and over 2 centuries gathered myth and horror around it. The machine's inventor, whose name it bears, did not imagine the cultural afterlife that would attach to his proposal. Similarly, the present question, how long consciousness persists after severance, will not live only in lab notebooks. It will travel into courtrooms, onto editorial pages, into classrooms, onto film stages. We should therefore be modest about what science can say, precise about what it does not say, and generous in acknowledging the feelings this subject wakes in us. The path forward is thus cautious and principled. Pursue research that reduces uncertainty while refusing to cross ethical boundaries. Gather and analyze historical and forensic records with modern tools. Use comparative physiology and ex vivo systems to map mechanisms. Deploy computational models grounded in human anatomy to constrain probabilities. And wrap all research in transparent oversight and public dialogue. Communicate results with care, precise language, trigger warnings, and an unrelenting insistence on uncertainty where it exists. In the end, the important truth is not merely a number of seconds. It is a commitment to rigorous methods, to ethical limits, and to telling the public what we know and what we do not know, without theatrical flourish. There is a strange tenderness in this inquiry. It asks, in essence, how fast the machinery of a mind collapses when its supply lines are cut. It is a question at once technical and moral. We answer it not with bravado, but with instruments, with archives, with conversation. We answer it slowly, as one might read the last pages of a long, hard book, to a restless child, turning the sentences carefully, mindful of meaning and of the sleep that follows.